Okay, so last time we stopped here at the linear programming. We just introduced an example. Is this working? We just introduced an example of how to maximize your happiness, and we made sure that you're well fed and stayed sane and survived. And we started phrasing this as a linear program. We use linear functions to model the objective, the quality of a solution, but also the constraints we used for formulating the constraints. We used linear equations. So you can see this here that we have what we have sort of intuitively phrased as our constraints, E equal or S greater or equal than 60, so studying at least 60 hours. This is a linear function in S in our variables S, P, and E, which simply takes S, P, and E and maps it to S. So it's just one time S. It's one form of a linear function, and we use these linear functions to formulate our constraints using inequalities and using equations. And so more generally, this is how a linear program looks like. We have variables, as in our previous example, we had S, P, and E. Generally, we have a set of variables. It doesn't have to be 3. We have an objective that we phrase using variables and use a linear function for this. So we said that your happiness can be measured as 2 times P, the time that you spent for partying, plus E, the number of hours you spend for everything else, like going grocery shopping and sleeping. And we have said that we have to satisfy certain constraints given here. So we have an objective, we have constraints formulated based on the same set of variables. One constraint is missing here. Anyone sees which one? Based on our previous example, we have a certain number of hours for studying, for eating, and for partying plus eating. What? The total hours, exactly. So we want to have the sum of these be summing up to 168, the number of hours we have in 1 week. And we require that all these variables S, P, and E be non-negative, because we can't spend a negative amount of hours in eating. So you can see in this example what the basic elements are of our linear program. We have variables. In the previous example, we had 3 variables, but generally there are n variables. We have constraints that use these variables and use linear functions in these variables to formulate inequalities, equations, as I said, using linear functions. And finally, we have an objective, which again is a linear function in our variables, S, P, and E in this particular example. And this objective can be a minimization, it can be a maximization. In the previous example, we tried to maximize happiness, but we have seen many problems where we try to minimize some value before. In this example, we can see that you also have sort of a mix of inequalities, and we have also an equality. And in this particular example, we have all variables non-negative, but that's not necessarily the case. There might be some variables in your problem that can also take on negative values. So this is the general form of a linear program. And let's see how an optimal solution to such a linear program looks like. So again, here's an LP. As we said before, now we're using 2 variables, X and Y, we call them. We have an objective that tries to maximize X plus 2 times Y. And we have 3 different constraints here in X and Y. And we have, again, that both variables need to be non-negative. So the nice thing about linear programming is that you can, at least in 2 dimensions, nicely visualize everything and get a good idea about a lot of the theory of linear programming. And this is what we're trying to do in this particular example. So here we're looking at a 2-dimensional plane. So we're only looking at 2 dimensions. We have 2 variables in this particular example, X and Y. We said that both variables need to be non-negative. So we only are interested in this upper right quadrant here. And now we have to go through our constraints and see what they sort of mean geometrically speaking. So let's start with our first constraint, which simply says that X has to be at most 20. So what that means is that I can draw a line in 2D And then I know that all the points that satisfy s x smaller or equal than 20 will lie to the left of this line. This is a half space. This is called in higher dimension. Higher dimensions, we wouldn't have a line, but more generally speaking, a hyperplane. But for our purposes, this is good enough. So we have a line in 2D that defines sort of the feasible set of solutions. So we know now that all feasible points, at least with respect to the first constraint, must lie somewhere here between, sandwiched here between these the y-axis and this vertical line. So they are non-negative in both x and y, and y, and they're to the left of this line because they need to be smaller than 20 in x. The second constraint tells us that y can be at most 30. So we do the same thing as before. We introduce now a horizontal line at y coordinate equal to 30. And then we know that all feasible points must lie somewhere in this rectangle here. Right? Because only these points satisfy that x is smaller or equal than 20 and y is smaller or equal than 30. So somewhere in there is our best point that we're interested in. The next constraint cuts off another piece. You can see that these points here, x plus y smaller or equal than 40, are defined by this line, which is setting x plus y equal to 40 is this line. And then all points smaller or equal than 40 lie to the left of it. So now, to satisfy all these three constraints at the same time, the points need to lie somewhere in this what's called a polytope. Okay, so all feasible points, all points that satisfy these first three, or all three constraints, and including the non-negativity, they will be all lying somewhere in this polytope, or in this intersection of half spaces, let's say. So every time we have sort of a line, we have one half space, and we take the intersection of these half spaces to get this this region of feasible points. So somewhere in there is the point that we're looking for that maximizes this and it satisfies all these constraints. And that's what's called a feasible region. So we just motivated all the points that satisfy all of our constraints, including non-negativity. They must lie in this green area called the feasible region here. And in 2D, this is very nice. In higher dimensions, it's a similar principle, but more difficult or impossible to visualize. Everything clear so far what a feasible region is and what points are really the ones that we're interested in? Okay, then so we now know among which points we should be looking for the best point. And now let's see how we find actually this one best point in this feasible region, and best in terms of this objective function here. So which point in this green region maximizes x plus 2y? This is what we're trying to solve here. So for this, let's first take this objective function, this linear function that defines the objective x plus 2y, and let's set it to equal to 0. Again, in 2D, we get a line. And this line, in this particular case, will go through the origin, and it will have this slope of -1/2. And then the meaning is that every point that lies on this line will have a value according to this function of 0. But for us, only one really is sort of is of interest, namely the one that intersects the feasible region, which would be exactly this point here. Right. So this point is the only one that this vertex here is the only one that we could consider because it's feasible, it lies in our feasible region, and it has a value of 0. Now, is this the best possible value that we could find? Well, clearly not, because we could start moving this line. So this should be parallel. I'm not sure if this looks parallel, but this should be a parallel line here, where we set x plus 2y, meaning the objective, equal 20. So now all the points that lie on this line will have a value of 20 according to this objective function, which is obviously larger than 20. So every point here on this line will be more valuable to us than every point here on this line. And again, we're only interested in those points that lie within the feasible region. So we're interested in points that lie on this line and intersect this feasible region along this line here. So basically all points lying somewhere here. These are sort of points, feasible points to us that we know now have a value of 20 in our objective. And those points, of course, we can't consider because they are, again, outside of our feasible region. And so we can keep on doing this, and we can increase the right-hand side here, set it to a larger value, and by doing so, get parallel lines that move upwards. And whenever you move it upwards, you get sort of larger and larger objectives in your in these points. So therefore, the objective or maximizing this function corresponds to moving this line here as far up as we can without leaving the feasible region. And how far can we go? So what is the, visually speaking, I don't need specific coordinates, but can you describe the optimal solution to this problem based on what we have said so far? Yeah. Oh, wow, you give me even a number. Why 60? But so the coordinates don't really even matter at this point. And I think they're not correct, but we'll see in a moment. But more importantly, can you describe the points that sort of corresponds to this optimal solution? So what you said correctly, we try to move this as far up as we can. And how far can we go? So what's the last point that we're touching? Maximum here, right? So you're looking at the left side, or do you look at the visual, I mean, the geometry? Maybe I didn't get it. Maybe you. This one? This one? This one. Yeah. Yeah, that's correct. So this is the last vertex that we're essentially touching before we're leaving. I don't know if this is what you meant. No. So which one did you mean? Was it one of these vertices? Within. So it touching is enough because we have smaller equal here. So the lines are sort of included in this. Is there a question? We're trying to find the one point that maximizes this. So this has nothing to do with the area of the feasible region. The feasible region just tells us this is the set of points. There's an infinitely many points in here. Every one could be our candidate. So we could, I mean, conceptually plug every point into this function and take the one that has maximum value. So that has nothing to do with the area of the feasible region. In this particular example, taking the maximum means that you want to move this line with this slope as far up as you can without leaving the feasible region. And as you said correctly, this would happen once you're touching this point. So this is, I think I have it on the next slide. Yeah. In this point here, you can see that this line, again, still supposedly parallel to these lines, is the last possible point where we touch the feasible region. And therefore, this point here, this vertex, where we touch this feasible region with this line is the optimal solution. Because everything, now if you would try to increase that value here, this right-hand side to something larger, the line would move up and we would sort of leave the feasible region and we would violate all our constraints. So this is where we get the optimal solution. The optimal solution will be a vertex of this, I call it polytope. I'm not going to formally define what a polytope is. This feasible region here, this green part, we're leaving this at one of these vertices, which means that that in general, the optimal solution to such a linear program will always be attained in one of these vertices of this green feasible region. Assuming that this green feasible region exists, we're not going to go into these details. So it might be unbounded or infeasible. These are other cases, but whenever we have sort of this bounded feasible region, we will have an optimal solution that is obtained in one of the vertices of this region. And the intuition is exactly this, because you can take this line in 2D, at least in high dimensions, a hyperplane that you can try to move as far as you can, and you will always leave this region at one of the vertices of this region. Yeah, so the optimal solution, therefore, I'm not sure about the coordinates of x and y, but the value will be equal to 70. And this is the point. This should be like, I think 10 and y equal to 30. So it's probably 10 and 30. Is 10 and 30, 70. 10 plus 2 times 30, yeah, 70. So this is our optimal point. And the optimal value of that point is equal to 70. And so we're not, I mean, we could spend another week just proving that this is generally true. We would have to actually define what a vertex is. We're not going to do this in this class. I just want to give you the intuition, the geometric intuition of what kind of problems we're really faced with here in linear programming, where we have always this bounded, or this green feasible region. And the optimal solution, the maximum value in this case, will be attained at some vertex of the feasible region. This is the theorem here, provided that we have such a feasible region. So it could be, of course, empty if you require, for example, that x smaller than or smaller or equal than 10 and x greater or equal than 50, then clearly both constraints can't be satisfied at the same time. So the feasible region would be empty, and then of course this doesn't apply anymore. It could also be unbounded, such that you get infinite large values of or optimals or values of solutions, and then this also doesn't apply. But for, let's say, nice cases that we saw in the previous slide, where we have such a bounded feasible region, there's always a vertex that takes on the optimal solution. Any questions so far? Because now, based on this insight that the optimal solution always lies on a vertex, let's try to come up with an algorithm that finds such a vertex. And I again only want to give you the visual intuition of this algorithm. It's a very famous algorithm. It's called the simplex method, which was introduced by George Dantzig in around 1950, or a bit earlier than that. It's a so-called hill climbing approach, where you start at some solution to your problem and then try to incrementally improve this solution. And it's exactly what the simplex method does. It starts at a vertex, because we know that we only need to look at vertices and are still guaranteed to find an optimal solution. So we start at a vertex, and then we look at, in each step, at the adjacent vertices. Adjacent in the sense that they are connected through an edge, as in the previous example. So we're thinking about this again in 2 dimensions. And then we simply jump to the next vertex that has the largest increase in the objective value. Okay, so here's an example. Here's our LP again with our feasible region in green again. And let's say that we start here at the origin. This is clearly a vertex of our polytope. This coordinates 0, 0. And if you plug in 0, 0 into our objective, you will see that the score here is 0. Right? Not surprising. So the value is 0. And what we will do now is simply evaluate the neighboring vertices, which in this case is this one here. This is a neighboring vertex, and this is a neighboring vertex. So let's start with the first one here. It coordinates 20, 0. If you plug in this point into our objective, we will see that the score is 20. 20 is larger than 0. But before going there, we will also check the other neighbor, which is this vertex here. This vertex has coordinates 0, 30. If you plug it in, you see that the score is 60. 60, we're trying to maximize, so 60 is larger than 20, so we'll jump in the next step to this vertex. So this is going to be our next vertex. We move up here to the next vertex. And then in this vertex, we do the same thing again. We look at the neighbors of this vertex. We're not moving back, so we don't look at the previous vertex. Therefore, only one neighbor remains, namely this one here. This is the only vertex that we have to consider here to the right. This vertex here to the right has coordinates 10, 30. And if you plug in these numbers, again, you see that the score of this solution is equal to 70. So 70 is the value, and you see 70 is larger than 60. So we'll keep moving to that next vertex and continue at this vertex here. Okay. We keep on doing the same thing. Now there's only one neighbor left, because we're not moving back. The next neighbor is this one here, again a vertex at coordinates 20, 20. If you plug it in, you see that the score is 60, and now 60 is smaller than 70. So we are already at a vertex with a larger score than the next one, and therefore we terminate, we stop here. We don't move to that vertex because it's not better than where we are currently. Yeah. That's what we said. So the optimal solution, there is always an optimal solution that is attained at a vertex. So we're not losing anything if you're only looking at sort of the vertices of this polytope. Yeah, that's the trick. I mean, it could be that your objective, maybe this line that we had in the previous example, lies parallel to one of these edges of your polytope, the bounded. And then it might be that all the points along this, for example, on this line are all optimal. But still, even then, there exists one or two vertices or multiple, at least one vertex that has the same optimal score. So it is sufficient to only look at vertices. And so this is one thing. So we're not losing anything by just looking at the vertices instead of the entire edges. And the second thing we have to consider now is that this, what we found now, by definition, is we call a local optimum, or in this case, a local maximum, because we're maximizing. Local in the sense that whenever I look at neighboring points, they are worse than where I'm currently are. But I can't exclude in general that somewhere far, far away from this point, there might be a better point that I didn't explore. In linear programming, that's not the case, or this cannot happen because of certain properties of this feasible region that we're not going to discuss in more detail. It is convex, but I'm not going to define what that means. Again, I want to give you only the visual idea. And the visual idea is the following. So if I find a local maximum, that means that if I draw the objective line, it will touch this point somewhere here. There should be a line. It doesn't look like one. And then it is local. When it's local optimum, it means that all the neighboring vertices will lie below this line. So all the neighborhood here will be somewhere smaller here, right? So, and if all the neighbors are below this line, because of the structure of this feasible region, it is convex. But visually, I mean, I think you can see this just intuitively speaking, that the whole region has to be on that side of the line. So it can't be that the local neighborhood is below the line and the rest of this feasible region, because it's an intersection of half spaces, it cannot be on the other side of the line. Meaning that if your local neighborhood is worse, the whole thing is worse. And therefore, every local optimal solution is actually a global optimal solution to your problem. And this makes your life much easier because you don't have to worry about a global optimization, because you just sort of try to find something that is locally optimal. And once you have found that, you know that you're actually done and there's nothing that can be better than this. Based on this nice property of being convex and having linear objectives. Yeah. Yeah, so this is a good question. And I mean, there's many things I haven't discussed. It would take a couple of weeks now to go through individual steps. How do you find the first vertex in general? In 2D, this might be easy. In high dimensions, that's not so easy. How do you go to the next vertex? You would have to introduce more general concepts like basic feasible solutions, where you have sort of a basis exchange, which corresponds to jumping basically from one vertex to a neighboring one. So there's a mathematical machinery that explains this. It's just linear algebra, essentially. But we won't go into any of this. But it's a good point. So all these questions have to be investigated if you really want to implement this algorithm and develop it carefully. So so how do you really, algebraically speaking, jump from one vertex to another is one question. How do you find the first vertex is one. Also, the strategy of always going to the neighboring vertex of highest value is also not always the best idea. Or very often you just take the direction of the largest objective, the rate of change, so with the largest range of change, instead of really looking at absolute changes. So there's many different things that I have not discussed and that are very important for the actual algorithm. But this is sort of the visual interpretation, visual idea that you should have in mind when talking about simplex algorithms. Any other questions? Yeah. No. Because I only have one lecture for linear programming, I didn't want to also discuss in integer. I mean, it's essentially it just means that you have additional requirements that some of your variables take on only integer values instead of being just real numbers. But then actually the whole problem becomes hard to solve. Okay, so let's look at an example, and one example that you have seen many, many times. Max flow. So now you're all experts in computing the maximum flow in a network after midterm 3. I think you can do this all better than me. So just as a reminder, you have this directed network G, and you have a source and a sink S and T. You have capacities on all edges, and you're looking for a flow F, which is simply a function that assigns real values, real non-negative values to the edges. And every flow by definition has to satisfy 2 constraints. It has to be smaller than the capacity of the corresponding edge. And for every node, you have to have what's called flow conservation, meaning that everything that comes in has to come out. That's just what's written here. So how can we phrase this as a linear program? How can we solve this using linear programming? So let's see, we have 3 ingredients. We said we have variables, objective, and constraints. What would the variables be in this case? What would you use as variables? This is generally, it's an art to come up with a good LP formulation. For more complex problems. For this problem, it's rather obvious, a rather obvious choice. So what is the decisions that you have to make, really? It's the flow, right? So how much flow do you push on every edge? So the variables will be simply the flow per edge. So the variables will look like this. We have sort of a variable xuv that needs to be non-negative because we said flow. I mean, you can see that flow is non-negative here. So for every edge, we are able to send some non-negative flow. This is what we capture in these variables xuv. Then what's the objective? Any idea how we can phrase the objective using these variables? Are we minimizing or maximizing? We're maximizing, exactly. We want to find the maximum flow. So which variables do we have to sum up in our objective? It's going to be a linear function. It has to be. Yeah. Exactly. So we sum all x variables that correspond to edges that leave the source vertex. So we simply sum over all x SU, where S is our source and SU is an edge in our network. And then we simply translate these 2 constraints one-to-one into linear equations or inequalities. The first one tells us that for every edge in our network, the flow has to be at most the capacity of this edge. So x is smaller or equal than CUV. This is the first class of constraints. And the second class of constraints models these flow conservation constraints, where we say for every vertex, except for the source and the sink, if we sum up all the variables that correspond to edges that enter a vertex V, this is here on the left, and we subtract all the flow that corresponds to edges that leave vertex V, then this has to sum up to 0. All right, this is the same as this one. So this is just flow conservation. And finally, we said that these variables need to be non-negative. So xuv must be non-negative, right? Here. This is our LP formulation. Does this make sense to everyone? How we model maximum flow as a linear program? It's very simple. And how do we solve it? Well, we can do it geometrically if we only have 2 edges in our network. But let's first look at an example of a specific network, because I noticed that sometimes this abstract class of constraints is not clear how it translates to a specific instance. So let's see how if we have a particular example of a flow network with these vertices. We have a source and a sink, and we have the capacities that are given here on these edges. How many variables will our linear program have in this particular case? Yeah, 11, exactly. We have 11 variables, 1 for every edge in the network. We will have, let's see. Oh yeah, okay, our objective. We said we sum up all the variables that correspond to edges leaving the source vertex. So we would have to sum up XSA, this one here, plus XSB, plus XSC. So these are 3 edges that leave S. So we sum up the corresponding variables. Then we have constraints. We have 11 non-negativity constraints that simply tell us things like XSA. So whatever we send from here to here has to be non-negative. So it's greater or equal than 0. We do this for all variables. So we will have 11 non-negativity constraints. We have 11 capacity constraints that simply tell us that in this, for example, again, the edge from S to A. Here we have capacity 3, so we need to have a constraint telling us that XSA is at most 3. So this is the capacity constraint. So of course we do this for all edges and replace the right-hand side here by the corresponding capacity of the edge. And then we have flow conservation. I don't know if you saw, but how many flow conservation constraints do we have? And why, in case you saw? How many flow conservation constraints will we have in this particular example? Yeah. 7. Any other opinions? 5. Yeah, it's 5 because we have because we don't count S and T. I guess you were counting S and T. Here we don't have flow conservation for all other nodes. We create one such constraint that would look like this. So for example, for vertex C, you would sum up the two edges that come in, XSC plus XDC, which must be equal to XCE, the flow leaving this vertex. And we do this for all nodes in this network. And this gives us a linear program. This is all we need, and we then plug it into or feed it into a so-called LP solver. So some software packages that typically implement some variants of the simplex algorithm. And they will give you a solution to this problem in no time, really, and tell you that the optimal solution, therefore the optimal flow in this network is equal to 7. So we could have saved us a lot of time and skipped sort of this maximum flow algorithm business by just, coming up with these linear equations and solving it. That's of course not true. This is just one framework. It's very powerful, but solving this problem combinatorially is of course much more efficient. Okay, but this is one way to solve max flow using linear programming. Any questions about that? See what comes next. So the question now we're asking, or we will be asking, is can we somehow prove that this flow is actually optimal? If you're given a flow of 7, is it optimal? Especially for max flow, we had such a thing. We had a very nice concept of duality between maximum flow and minimum capacity of cuts. We said that every cut, or the capacity of every cut in our network, will be an upper bound on any flow in our network, and therefore whenever we find sort of a matching flow to a matching, or whenever we can match the value of a flow to the capacity of a cut, we have found the optimal solution. And surprisingly, something very similar exists more generally for linear programs, as you will see. And this is called duality. So for a duality for linear programs means the following. So consider this linear program again. I think it's the same that we had before: objective, constraints, non-negativity. And you can see if you plug in the solution here, x1 equal 10 and x2 equal 30, this will give you a value of 70. So this is easy to tell. So the optimal solution to this will be at least 70, right? It could be better. We found one solution that has score 70, so it must be at least 70. Can you find an upper bound in this? So do you know, similar to max flow, is there anything that you can use to prove that this solution cannot exceed a certain value? So for this, the idea is to use a linear combination of your constraints to derive a new valid inequality for this set of solutions. In this particular example, consider taking the first inequality, this one here, and add 2 times the second inequality to it. Okay? So what do you get when you add the first one to 2 times the second one? You get, well, x1 only occurs here in the first constraint, so the sum will only have x1. x2 only is contained in the second constraint, which we multiply by 2. So we will have 2 times x2. So we have x1 plus 2 times x2. And we do the same thing for the right-hand side. We add it up, multiplying by 1 and 2. we get 20 plus 2 times 30, which is equal to 80. So from these two inequalities alone, we derive a new inequality, a valid inequality for our set of feasible solutions. And now if you compare the left-hand side of this inequality to the objective, you can see that it's identical. Right? So what we have now created using this linear combination of our constraints is something that looks exactly like our objective. And at the same time, we know that this objective must be at most 80. So this is basically an upper bound on the objective. We know that if we are following these constraints, the sum can be at most 80. So this doesn't match exactly our current solution, but we know that the optimal solution will lie somewhere between 70 and 80. We don't know where, but we might not be too far away really with our optimal solution 70. It could be 70, it could be 80, or something in between. So to sort of solve it for this particular case, let's try to formulate what I've just done here in this example more generally. So what we did is the following. We started from a set of constraints, and this is exactly the same constraints as before. I have aligned them a bit nicer now in the corresponding columns. It's a bit easier to read. And then what we have done is we have added up two of them and multiplied them with a certain constant. Before we had set y1 equal to 1 and y2 equal to 2 and y3 equal to 0. But more generally, we could take any linear combination of these constraints and add them up. And we can add them up with only non-negative variables y, because if you would use a negative value here, we would sort of switch these inequality. The inequality would change its direction, and we would not be able to make certain conclusions. So we want these coefficients here, these variables y, to be non-negative, to preserve the direction of these inequalities that we're multiplying. So if we do this, what we get is this here. Let's see. So we have multiplied the first equation with y1 and the last one with y3. So these are the only ones that contain x1. So if you look at x1, the variable, it will be multiplied by y1 plus y3. Right? This is what I get for x1. Now, if I do the same for variable 2 occurs only in the second and the third inequality. So I'll get y2 plus y3 times x2. There's no y1 here. Right? So this is simply adding up or creating the linear combination of the left-hand side of these inequalities using these coefficients y1, 2, and 3, and resorting by x1 and x2. This is nothing else here on the left-hand side. Then we do the same thing for the right-hand side. So we multiply all these right-hand sides with the coefficients and get 20 times y1 plus 30 times y2 plus 40 times y3. And this is how you create a new valid inequality for your solution. Okay. And so in the previous example, what we did then is we tried to, we actually found coefficients such that this here looked exactly like our objective. Right, we had x1 plus 2x2, and then we immediately got an upper bound. But more generally, we would have to set this here, these variables, such that we get something that looks exactly like our objective. This is here our objective. So we want the left-hand side, this one here, to look exactly like this. That's what we did before. And we do this by setting the first coefficient of x1, which is y1 plus y3, equal to 1. And we set the second one, y2 plus y3, equal to 2. And this gives this means that what we get here will be an upper bound. That this here, if we make sure that this holds, will be an upper bound on the objective, because it will be exactly looking like this. But since we're only interested in upper bounds and not necessarily in something that matches exactly our objective, we're actually free to set this to anything at least to 1, and this at least to 2. It doesn't have to be exactly 1 or 2. It can be anything that is greater or equal than 1 or 2. These ones. So this is sort of generalizing a little bit what we did before. Before we said, okay, We pick these coefficients such that we get exactly something that looks like the objective. Now we get something that's a bit larger, that could be larger than our objective, but not smaller. Okay, but then we're actually done. We have obtained an upper bound, because we can now say the objective, this is this here, this is the objective of our linear program, will be smaller or equal than this term, which is the left-hand side here, provided that we set these variables to at least 1 and at least 2. So if we set these variables 1, 2, 3 to these, such that y1 plus y3 is at least 1, and y2 plus y3 is at least 2, then this here, this term will be greater or equal than our objective. So that's what's shown here. So x1 plus 2 times x2 is smaller or equal than this. And then I have something from the right-hand side. I get an upper bound here on this term, which I can plug in here and see that this here will provide an upper bound on this here, on our objective. And this is what we did. So before we did the exact same thing, and our right-hand side was, I think, 80. Yeah, this I think was, yeah, we picked y1, y2, y3 such that this here on the right-hand side gave 80. Now what you can see is that I can choose y1, y2, and y3 however I like, as long as I'm satisfying these constraints. And whatever I do, I will get something that is an upper bound on my objective. So I could say, I set all these 3 variables to 1,000, and I get a really, really large value here. And I know that this large value will be an upper bound on my objective. So my objective cannot be larger than this. But of course, I'm interested in something that is as close or as small as possible. I want to have a very tight upper bound. And that's why I'm trying to find coefficients y1, y2, y3, such that this side here is as small as possible. In other words, I'm trying to minimize this function in y1, 2, and 3 under the constraints that y1 plus y3 is at least 1 and y2 plus y3 is at least 2. And this gives us a new linear program. So this is the surprising thing. Everything that we have said so far leads to one linear program in these variables y1, y2, y3, using these constraints and using this as an objective. I think I showed this on the next slide. Yeah, so this is summarizing basically what I just said. This was our original linear program. This was a maximization problem under these constraints. And we created a so-called dual linear program where we try to minimize this function here in y1, y2, y3 under these constraints that we had before. And all these variables had to be non-negative. So just finding a linear combination of our constraints and making it look like sort of an upper bound to our objective in the primal LP, we obtain again a linear program where we can say that any feasible solution, any coefficients y1, 2, and 3 that satisfy these constraints, they will provide an upper bound on any solution here by construction. This is how we came up with these constraints in the first place. So these constraints here, they are formulated such that they will give an upper bound on the objective. So everything here will be, everything feasible to this one will be an upper bound on this one. And since we're minimizing this here, we're trying to find the smallest possible upper bound on the optimal solution in the primal linear program. And this is what's called a dual linear program with respect to the original so-called primal linear program. So here's sort of in more general notation what we just did. So more generally speaking, you have a primal linear program. And for the purpose of this class, we're assuming that we're maximizing here a linear function. We have coefficients c in variables x1 through xn. We have many constraints here indicated by these rows. And we have coefficients a11 through a1n for the first row and so on. And we require that all these variables are non-negative. So you can see that our previous example followed exactly the scheme with certain, I mean, most coefficients or several coefficients here were 0. So this is what I'm referring to as this one. This LP, this primal LP has exactly the structure. So here a11 would be 1, a12 would be 0, a21 would be 0, and a22 would be 1, and so on. This is what's written here, basically. And the dual LP looks like this. So this is how we generate the dual linear program. based on exactly what we have just done. We found these so-called dual variables, what we used as coefficients for our constraints. We set they're all non-negative, so the dual variables need to be non-negative in this setting. And we said that for every constraint in the primal linear program, we introduce one variable in a dual linear program. So we'll have m many variables because we have m many constraints in the primal. And then we sum them up. So we do this for every variable. So if you look at the first variable in your primal linear program, x1, I'll create one constraint in my dual linear program for that variable. And this is exactly the first constraint, where I simply sum up all these coefficients here of x1. I get a11 times y1 plus a21 times y2 and so on, all the way down to am1 times ym. And then I'm simply doing the same thing for the right-hand side. And I claim, or I want this right-hand side times my coefficients to be minimized. This is the objective of my dual linear program. So the dual linear program is just sort of the right-hand side, taking the linear combination multiplied by the y coefficients of the dual linear program. So this is really exactly doing this here, where we have these dual variables. We introduce one variable per constraint, and we introduce one constraint here for every variable, x1 and x2 in this case. And we have an objective that is really just obtained by taking the right-hand side of our linear program. So you should have in mind really this first example that we did, where we tried to take linear combinations of constraints to get an upper bound on the objective. But once you have this understanding and you have such a primal linear program given, then creating a dual is a very mechanistic approach. Even if you don't understand anything about dual linear programming, just memorizing, how you generated it by creating one variable for every constraint and creating one constraint for every variable, comparing it to the coefficients of the objective. Here, this is the objective value 1, objective value 2, and then creating an objective that contains basically the right-hand side from your primal LP. This gives you a dual linear program. So this is a very mechanistic approach to creating such a dual linear program. Any questions? So this can be a bit, maybe you have to sit down and think a bit about this for a bit. I mean, I recommend going through this example and really fully understand how the original motivation was. This is the main part, really creating this linear combination such that we generate an upper bound on the optimal solution. And then we sort of just generalize this to coefficients y1 through y3 and did the exact same thing, sort of using variables instead of numbers. And that's what you get here then, basically. And once you have this understanding, just try to do this mechanistically, try to generate a dual linear program given a primal linear program. So this is the general form. And okay, so the next step. So we said now that by construction, the way we constructed this dual linear program, any solution to it will provide an upper bound on any solution of the primal. And this is similar to capacities of cuts versus flows in networks. And there we had this additional property that they actually match at some point at the optimal solution. So let's see if that's what's happening here. So if I take the optimal solution for the primal linear program, what we had before actually is optimal. So setting x1 equal to 10 and x2 equal to 30, we get a score of 70. And you will see this is optimal because of the following. Because now if I compute the optimal solution of the dual linear program, it turns out that it's going to be setting y1 to 0, y2 to 1, and y3 to 1. And if I plug this into my objective, I get a value of 70, which matches exactly the score of my optimal solution to the primal linear program. And therefore, I know that 70 is actually optimal because I said before, by construction, every solution here provides an upper bound here. And since I have found something that matches my upper bound, I know that both these are optimal. So 70 must be the optimal solution to my linear program because I have found a matching upper bound really through my dual linear program. The exact same principle as in max flow versus min cuts, just in a more general framework. And in fact, this is Not a coincidence. So this is summarized on this slide. This is basically the situation we had for max flow versus min cut. I can sort of draw all the values of possible flows here on the left side. And then the capacities of all valid cuts in my network will be all larger. So they lie somewhere here on the right side. And at some point they're matching. So the max flow meaning will be equal to the min cut. So they match at the optimal solution. Right? And something similar is true for linear programs. For linear programs, we have what's called weak duality, which simply says that any feasible solution to the dual linear program is an upper bound on any feasible solution to the primal linear program. So let me draw this. This is this picture here. So any feasible solution to the dual here will be lying to the right of any feasible solution to the primal. This is what the weak duality says. And the strong duality theorem tells us that actually there exists this point where these two match. So the optimal solution of the primal will be always equal to the optimal solution of the dual. This is one of the core theorems in linear programming, which we are again not going to prove. But this shows you that what I've just shown you on the previous slide is one particular example where the optimal solutions to primal and dual matched is not a coincidence. This must be always the case for every pair of primal and dual linear programs. Okay, any questions at this point? Okay, then the last thing I want to tell you about is what's called a standard form. So there's, I told you in the beginning that a linear program can either maximize or minimize a linear function. You can have inequalities, you can have equations as your constraints, and you can have variables that are non-negative, but you can also have, or that are required to be non-negative, but you can also have variables that are free to take positive as well as negative values. And the standard form is one specific form of a linear program, a more restricted form, but one can show that essentially any form of a linear program can be converted to such a standard form. And then it makes it much easier to discuss certain types of algorithms, especially the simplex algorithm needs to have the standard form that I'm going to introduce here. And it makes certain assumptions about this form. So many LP solvers, the most popular ones, I believe, are, I'm not so familiar with the other ones, but I'm familiar with Gurobi and also with Cplex, another one from IBM. These are sort of the most popular LP solvers. And LP solver simply is for us, it's just a sort of a black box where you input a linear programming formulation. It gives you assignments to variables and tells you that this is an optimal solution. It gives you a score. And as I said, they require LPs in what's called a standard form. And a standard form looks like this. So one thing about this is here, I'm using a slightly different notation. So maybe before talking about what the standard form is, let me introduce this specific notation that's very common for linear programming, because this, of course, is much easier to write than something like, where is it? Something like this. This is sort of writing it out in full, but this is sort of a shortcut here. This is much easier to write down and to read. So we have, essentially, we're using here in the objective a dot product between two vectors, and here a matrix vector products. Here's an example what that means. So here on the left, this is our sort of form of a linear program that we have considered before with linear functions, and in this case, in 3 variables in the objective, and we have 2 equations as constraints, and all these variables are non-negative. And I can rewrite this sort of in a shorter form by using sort of this this dot product presentation. Dot product. How do I get rid of this mouse here? Okay. So you can see that here, this dot product means 1 times x plus 3 times y plus 4 times z, which is sort of a different way to write this. This is what this means. C transpose x looks like this, but it's really the same as this. And instead of writing every equation out here, I just collect all these coefficients in one matrix, in this matrix A. And here will be our variables. So if I write this out, if I multiply this, you will see I get the exact same thing. I get x plus 2 times y plus z is equal to 5. This is exactly this constraint. And if I take the second row of this matrix and I multiply it with this vector, you get 2 times x plus 3 times y plus 1 times z equal to 6, which is exactly the same as the second equation. So this is just a shorter way or more easier way to write this down in matrix and vector form. This is what this represents. But more interesting for us really is the standard form. And the standard form means 3 things. So A, the objective must be a minimization. So we're not maximizing in a standard form. Standard form always means we're minimizing. And our constraints will be always in equation form. So we don't have inequalities, we only have equations. And the last thing is that all our variables, so this is x is a vector here of dimension n, we have n variables. This has to be non-negative. So all variables need to be non-negative. We don't have any free variables in this model that can also take on negative values. So this seems to be a more restricted form of a linear program, because we really have to use only non-negative variables, only equations, and only can minimize. And then the rest of this class, I want to just convince you that that's not really a restriction. So let's see how we can convert any linear program to this particular standard form. So the first thing is the objective. We said we can only minimize. Is this a restriction? So let's say you're trying to maximize this function subject to these constraints. Can you rephrase this to a minimization problem that has the optimal objective, that has the optimal, sorry, the same optimal solution? Yeah. No, the dual gives you, in this case, a lower bound, but it doesn't give you sort of, you want to have an LP that is completely equivalent. It gives you, there's a one-to-one correspondence between feasible solutions, and the optimal solution should be identical. I got the same response this morning in the first class also, by the way. Any other suggestions? From previous homeworks and previous exercises and examples in classes, this must be very obvious to you now. Yeah. So a large constant and subtract something. So this sounds very similar to what we have done with I think metroids and minimum spanning trees, I believe. Here it's much easier. You don't need to have positive values, which we had to have in metroids. This is why we had this positive constant. But here we can just multiply everything with -1. So instead of c, we take -c, and that's it, right? So instead of maximizing c, we're trying to minimize -c. That should give you the exact same, right? So the constraints stay the same. We don't change anything here. And you can see that the score is simply multiplied for every solution that has a score of x. No, x is a bad example of u. The new score will be -u. And therefore, instead of trying to find the maximum one with respect to c, you try to find the minimum one with respect to -c. Does everyone see that? This is a very standard trick in many that occurs in many flavors, different. We had this, I think, for spanning trees, for metroids, and for other cases where sort of minimizing and maximizing are related simply through multiplication with -1 or so. And I think in metroids, we had to add a positive constant, or we did add a positive constant to make these values again positive. But this is not a requirement here. These coefficients can be anything. They can be negative and positive. Everyone sees that? This is true. That's equivalent. Okay, this was a little warm-up. Now it's getting a bit more interesting. So what if you have inequalities? So you have this linear program, and let's say you're minimizing now. You have non-negative variables. In fact, you only have one variable. And you're trying to, and you have this one inequality that tells you that x1 is at most 20. What do you do then? Any suggestion? Yeah? Multiply c by -1. So if you multiply this by -1, you would have to maximize again to get something similar. But it doesn't help you anything with the constraints here, right? So you want to have this to be equal. So you have to rephrase this such that you get a solution that is always equal to 20. That's a bit less obvious. So we introduce what's called a slack variable. The slack variable S here. It's a non-negative variable that we simply add to the left-hand side, and then we simply switch this inequality to an equality. So instead of requiring x1 smaller or equal than 20, we'll say that x1 plus some slack must be equal to 20. So this variable S simply captures all the slack of x with x1 with respect to 20. So that means that, and of course it's free, so we don't have to pay anything for that S. We can do as much as we want. So this is just a trick to make sort of to fill up the gap between whatever x is and whatever the right-hand side tells you it should be. And you can see that they're equivalent in the sense that whenever you have a solution here that satisfies x1 at most 20, then there exists a non-negative S such that x1 plus S is equal to 20. Right? So if x1 is, let's say, is 16 in one of your solutions, it's feasible, then you can still keep x1 as 16 and you simply add 4 to S to fill it up to 20. And the score is, of course, the same because S is for free and you still have the same value of that solution. So every feasible solution here corresponds to a feasible solution here of equal value. And the same is true in the reverse direction. Whenever you have something that satisfies that x1 plus S equal 20, then x1, because S1 is S is then negative, x1 must be at most 20. Right? So we can sort of convert back and forth between solutions to one or the other LP. So this is what happens if you have a smaller equal relationship here, an inequality that looks like this. What do you do if you have a greater equal in this case? Yeah. Yeah, exactly. So we keep that variable. We call it now surplus variable instead of slack variable, but it doesn't really matter. But the purpose is very symmetric. We're trying to simply subtract everything that exceeds 20. So instead of plus, we will have a minus here, and we will simply subtract something non-negative. Same logic applies. So whenever we have something that is larger than 20, if x1 is 22, then x1 minus S, then S would be, you could set it to 2 and you get exactly 20. And you get a solution again of the same score. So the values are again identical. And of course, this applies in both directions again. So what's the last thing that's missing now to make every LP into standard form? We have taken care of the objective. We have made sure now that we can convert every inequality into an equation. What's the last piece that's missing? Yeah. Exactly. Make sure that all the variables are non-negative. Let's look at a counterexample. This one here. Here's again a linear program. It's not yet in standard form. We don't have minimization. We don't have equations, but we do have these variables that are allowed to take on negative values, namely x2 in this example. So this example again has two variables. x1 is non-negative as it should be in standard form, but x2 is allowed to take on any value, including negative values. And that's why this is this is one of the reasons it's not in standard form. So what do we do if you have such a case? If x2 is free to take everything, how can we make sure that we can get this into non-negative variables? So that's not as easy to see. Think of, in this case, you will need to introduce new variables. Yeah, we did this before too, actually. Yeah, we introduced surplus variables or slack variables. Now we want to introduce variables to essentially express that x2, which can be positive or negative, that x2 is the difference between two non-negative values. This is the trick. So you'll consider that every real value can be, or real valued variable can be expressed as the difference between two non-negative variables. That's all you need to know. So what you really do is you introduce two variables. So for x2, which is free, you take two new variables, x2 plus and x2 minus, that are both required to be non-negative, and replace x2 both in the objective and also in your constraints simply by this difference between x2 plus and x2 minus. So why does this work? Well, if you look at any feasible solution to this linear program, x2 can take on any value, right? It can be positive or negative. So let's say it's positive, so meaning that x2 could be equal to 26 in a solution. Can you convert it into a solution of this formulation of equal value? And the answer is yes. If x2 is equal to, let's say, 26, then I can set x2 plus also to 26, and I can set x2 minus to 0, right? Then x2 plus minus x2 minus has the exact same value as x2, namely 26. And that's why the objective will be the same, and also the constraints take on the exact same value as previously. The second case is that x2 here could be negative. It could be having a negative optimal score, a negative optimal value. x2 could be equal to minus 16. What do you do then? If x2 is minus 16 here, you could set x2 plus to 0, and you could set x2 minus to 16, plus 16. And then you see again that this difference will correspond to minus 16, so the exact same value that x2 took on, and therefore all the objectives and the constraints are equivalent between the two, and the score is the same. And I did this by using only variables that take on non-negative values. And so this does the trick, and we're sort of replacing one variable by these two variables, simply exploiting the fact that the difference between two non-negative variables must be can be used to express any real valued variable. And it's true in both directions. So whenever I cannot express more with this LP than before, because everything you do here, if you come up with very crazy values of plus 46 and minus 32, or sorry, plus 46 and plus 32, then you get the difference between the two, and the difference always can be captured by this free variable x2. x2 can then capture any difference between these two variables. So you cannot express anything in this linear program with these two extra variables that you cannot express in the original linear program with this free variable x2. And that's the whole idea. And that's why the optimal solutions between these two are equivalent. And I think this is the last slide for today. Yeah. I'm a bit done a bit earlier than I was with previous class. Maybe there were fewer questions, but I'll stop here to be in sync with the other class. But you can use this time if you have any questions about this class, if you have any, or about this topic today. If there's anything about duality or standard form or the geometric interpretation of linear programs, you can ask now, and otherwise we just meet again on Thursday. Was there a question? No. Good. There's no question then. Thank you, and see you on Thursday for our last class. Oh, yeah. Sorry? Yeah. Right now I go back and I put on the slides on canvas. The average around 11. I think no, we didn't post that. Maybe we didn't. It's 11. It's in an email. In grade scope, you say? Grade scope was in an email. I don't know if you got that, but it should say I think median and average was 11, around 11. Yeah. Sorry? The final review, I mean, it's the same thing that midterm. I mean, we had 3 midterms. It's exactly the same as the 3 midterms. Plus, yeah, so we have, I think, besides 3 midterms. So I posted a recitation for linear programs so that you can practice linear programs. So I recommend going to the recitation tomorrow also. Homeworks we had, I think the last one did not include, no, it didn't include obviously linear programming. It included only dynamic programming. So what's new really to the final will be mostly dynamic programming. So this was the focus since then. We had a few other things, I believe, like Born formulas, but I will make an announcement. So dynamic programming will be the main part that is new, and there's we had different examples. And we had one class of linear programming, and on Thursday we will have one class about computational hardness, but it's going to be obviously very high level. We're not going to go into depth into this. So basically only what's covered here and what you do in the recitation tomorrow then. Yeah. It's going to be, it has two parts. It will have one or two open-ended questions, but I'll make an announcement today or tomorrow.